Car collision avoidance system. Philip, Kyle, Shannon, and Rosmi. Okay, Casper. We're a collision avoidance system for the prevention of exterior repairs. Unlike Safe for Drone, Casper is completely grounded, so he only rolls around in a little car. In a nutshell, Casper is designed to avoid, as of right now, flat walls. It has a little bit of difficulty with anything in the corner, just to the nature of placement of the sensors that are on it currently.
Yeah, so our product essentially, if it senses a wall or something, it will automatically turn, similar to the previous project, but just in a car.
So here's the outline for what we're going to go over today. We're going to introduce ourselves more personally than we have so far. The impact that collision avoidance system have on society, what the contributions and originality that we've kind of put into this project, any standards that we've used and kind of want to adhere to in the future, design solutions that we had to come up with, and then along with revisions that we had to make to those designs due to time constraints and issues. We're going to go through some testing that we do have, some technical skills that we learned while doing this project, and system overview of both hardware and software. Finally, we're going to end it with a little video of Casper actually working in action.
I'm Kyle Krevy. I'm the lead electrical engineer. I'm interested in electrical design and power systems.
I'm Rosenberry, computer software engineer, specializing in design and coding.
As you might have noticed, Shannon's not here, unfortunately.
Currently in softball.
She currently has a softball game. Wish her luck. I'm Phil. I'm the team leader, and I'm also the lead software developer.
So the societal impact of our creation is that it will prevent a lot of costly car collisions from occurring. Right now, the average claims for bodily injury in a car accident is 15,443. The property damage claims average 3,231. We cannot bring those figures to zero, but we believe we can significantly reduce them with the collision avoidance system. And in 2010, the property damage accidents caused 71.5 billion. So if we can reduce those, it can have a huge impact on drivers and safety and potentially even saving lives. One other idea we originally had was we were going to have a foam displacement in the car, so if something were to come and hit it, foam would deploy and it would act as a cushion, preventing any damage from occurring, and it would just clean off the foam at the end. That was an original idea we had. Unfortunately, because of time, because of money, because of various constraints, we didn't follow that through. We stuck with just the distance sensor sensing a wall, and then the car would move.
Or it's been built into the system that it can be expanded to handle such a deployment system being attached to the car itself.
Alright, so these are a few of the standards associated with our project. So we have the lane departure warning system. It's basically a warning system for any vehicle departing from a lane. It would sense any incoming danger that is coming towards the vehicle, and it's solely dependent on the driver to make a safety decision. We have the forward collision warning system, also known as pre-cache. it detects any collision that is coming towards in front of the vehicle. Blind spot is basically where the driver cannot see. The system detects any incoming danger as well. But our collision system goes above and beyond these standards because it's automated and it makes the decision for you instead of depending on the driver making a safety decision. So, our design solutions. So basically, because of funding being our number one constraint, we made a model car, but it is scalable. We've recycled parts as well from the schools, such as like a few, like 2 of our sensors and like the component for the structure of the car. We also had to create a 9-volt power supply that we used 7 1.3 volt batteries, and we used a 5-volt converter because we have certain devices such as the Arduino that needs 5 volts. Preliminary design revisions. So the original design, as we spoke before, included a foam dispenser along the rear of the car, but due to like technical difficulties with our motor and coding and stuff, we didn't have much time to implement it. At first we thought of having a liquid spray as well as the foam deployment, but we thought about it and the time it would take for the foam to dry and prevent a collision would be very long compared to having a Tempur-Pedic square that could be deployed and somewhat refrain from damaging the car as much. So we excluded that design from the project this year, but the future class can use this as a way of getting some type of idea for their project in the future.
So to get kind of one thing out of the way, well, a couple things out of the way, we could not have completed the entirety of this project by ourselves by building it from the ground up. So we wound up having to recycle a bunch of parts from a previous project. So we had to, when we first received it, we had no idea what was going on inside this car. So we ripped out everything and figured out what we could and could not reuse. So most of what's on the previous project side, we actually were able to reuse. We had to upgrade our Arduino though to an Arduino Do because it required more analog pins to read in data from our distance sensors. So the total, our current cost for this past year was only reached up to 144, some change. This kept us under budget, but the total overall cost, including everything that the previous years had done, comes up to about 375 and change. So, arguably the two biggest components of our design was implementing 2 specific tests. One was getting the distance sensors to work properly. We needed all of them to be able to read somewhat accurately, up to a range of about 80 centimeters. Some of them could go beyond, some of them did not. The next was the integration test. We actually had to make sure that we could use our motor control with our Arduino board because we didn't have any knowledge of how that actually worked. So both managed to pass. Here's the video of of us testing one of the sensors. So what we did was we took a plane of plexiglass, put some white paper on it, and then we put it up next to a meter stick, and integrals of 5, we checked each centimeter. What we just saw was it reading about 50 centimeters consistently at the 40 centimeter mark. This was offset since we started this is actually a rough, pretty good actual distance reading because we actually offset the meter stick by starting it beyond the furthest wheel from the car. So this is the graphics data we actually recorded from doing such and such. As you can see, two of the sensors, H and R, they cut off sooner than we expected it to. Specifically H did, so we had to order more sensors to replace these. As you can see, they do a roughly good job of reading accurately, say each sensor up to about 80 centimeters and beyond. We really only needed them to go in the end between 20 and, well, not 20. Here's the integration test. This is the car moving with the motor control.
These are the early stages, by the way.
So for our project, we've gained a couple technical skills on Arduino. It's something we've been familiar with in our past courses, so we used that with the coding and motor controls of our system. We also used AutoCAD. We've gained knowledge out of the classroom with this, and we've created like 2D and 3D models of our system, the power schematic and the data schematic.
So this is the schematic of our power supply. Basically, you have a 9-volt battery. That battery powers a power strip. That power strip is now energized at 9 volts. So you have a bunch of things being powered. The Arduino is powered at 9 volts, the fan is powered at 9 volts, and the motor control is powered at 9 volts. One of them goes to a 5-volt power transformer and goes to a 5-volt rail. So all the other items that are powered from 5 volts are powered off that 5-volt rail. So the hall sensors and the motors and the distance sensors are all powered from 5 volts. So from the 9-volt power supply, it goes to the 5-volt transformer, and then powers 5-volt rail, powers everything that needs 5 volts.
So the data schematic, real quick, everything's synced to the Arduino. Each of the sensors, each of the motors, the hall sensors on the motors, and the motor control has 8 pins that we'll get into shortly to be controlled by the Arduino.
So,
Where are located the sensors?
which right here? Each P1 is a distance sensor. So this is a distance sensor right here.
Okay.
So blue, distance sensor, blue. So
Description of the sensors.
the what do you
One cover description of the sensors.
Oh, how they work?
Yeah, how they work, what kind of sensors you use.
Yeah, well, the RF sensor, so it sends out a RF wave.
What sensor?
So RF sensor.
What is it?
So
They're optical laser distance sensors. So they work by
they
shooting
send out
out.
a signal, then it bounces back. So
Even in the side you put optical sensors?
Yes.
Okay, here's what.
well, it bounces. It sends out a signal, then that signal bounces back to the sensor, and that's how it determines how far it is. So this is our actual motor controller. This is the pin layout for it. So each pin does something different. The top pin VM, that actually powers the motors. So that's our 9-volt voltage input for the actual motors to spin. The VCC is the logic voltage, and that actually powers the actual microcontroller itself. A-in-1 and B-in-1 and A-in-2 and B-in-2. Those are the logic inputs that connect to actual Arduino, so that actually determines whether it's going to go forward or backward. It sends a signal. Standby we use to you can shut off the entire pin at once. The pulse width modulation, which is PWM on the motor controller, that'll determine the speed. And then A1, B1, A2, and B2, those are the voltage inputs for the motor. Now this slide shows the motor controller logic input. So any input, this table gives you the output. So if you have a high, or high or low, it'll tell you that your output might be a short break. You go to the table, it'll show you every possible input to get your desired output. This right here is the 5 stages of the motor changing states. This is kind of under the hood, so you don't really deal with it directly. It's an H-bridge. We deal mostly with the pins, but this is what goes on underneath. Just a quick explanation, it uses a short break when it wants to stop. In order to do that, it doesn't go directly from state 1 to state 3. because you could have a short along the two left transistors. So it has an intermediary state 2. What it essentially means is the top left transistor fully closes before the bottom left transistor opens. So it makes sure there's no short circuit along the left side, because the transistor doesn't just open automatically and close automatically. It makes sure a transistor is fully closed before opening the other transistor. And this is basically just going back from the short circuit break to forward motoring. It still has that same in-between state T4. It makes sure that the transistor is fully closed before opening up the new transistor. It's the H bridge.
Okay, so this is the operating system for Casper. It runs, and it was made entirely through the Arduino IDE. So to begin with, we have to set up the pins. Distance sensors 1 through 8, they're all inputs. And then we have each of these. We have the standby pin, the pulse width modulators, and the A and B in pins. Those are all outputs from the Arduino to the motor control. Then we're going to run into the loop. And in the loop, I'm calling forth functions that I will state very soon. So C1 through C8 are actually calculated, are the calculated centimeters from the distance sensors. Each one goes through the way this distance sensor is set up in the code. It reads from the back C1, distance sensor 1, distance sensor 2, 3, 4, 5, 6, 7, 8. So so logically, to make everything easier for the Arduino to understand, we've created a back state, a right state, a front state, and a left state, effectively turning each of the sensors on each of the two sensors on each side of the of Casper into effectively one redundant sensor. It works quite well. So this is the sensor state. This is what each distance sensor calls in order to check the distance and saves the result as one of three, well, right now two, one of two separate states, goo being good, so that's send it 2, and avoid being 1, that's 1, and that is determined by how close the distance sensor calculated something to be. If it's greater than 15 centimeters, it's going to be good. It's not going to worry about sending an avoid signal to the actual Arduino. If it's below 15, but in between 0, because it's below 15, it's going to send an avoid signal. And due to the nature of the Arduino itself, it actually sometimes the distance sensors read a very large negative number, so it's also trapping it between 0 and 15. This is the side state. Same idea. It reads in two sensors, the ones before it, and determines whether it should be in a stop state, an avoid state, or a go state. This is another of the loop. This is really the main brain. We have to conduct an exhaustive search in order to determine what Casper is actually going to do next. So, this is an example. If all of the states are reading good, then it's just going to go straight. If it reads that the left state is in a void, it's actually going to turn the car right. If it reads that the right state is in a void, it's actually turning the car left, and so on and so forth. This is an example. This is the straight function I used. To turn right, you would switch the motor B to, instead of being high then low, it would be low then high. And for left, we'd switch A from high to low to low to high. Here it is.
This is our system in action.
So you see, senses there's a wall, and it moves. So it will not collide into the wall.
reference system used. Any questions?
That's Giaco's?
Yeah. What is the accuracy of your sensors? The accuracy.
They're about 95% accurate up to
The range.
from about 0
Range
to
accuracy.
I think like 80.
it goes up to about 80
80
centimeters.
centimeters?
Range accuracy.
Yeah, 80, you can read up to 80 centimeters accurate.
8 centimeters can be up to
80.
80.
80
80,
centimeters.
80 centimeters.
80 centimeters accurate.
Yes.
Number one. Well, number two, lateral. Do you have any data lateral collision avoidance?
Yeah, there's distance sensor on the side. Yeah.
Reads
I didn't see. I didn't see.
the
In the video or the schematic?
Yeah, no, on the video, real time.
what's that?
I don't see lateral. It also
It looks like it hits the first time, but it's just no. It's just the angle because you're looking at it at an angle. It's
Yes.
going behind it. It's not the best video
The
angle.
best thing to do this experiment, to this demonstration is to do 16. 216 we have special corridors,
Uh-huh.
good corridors, where right and left there are wood walls, and to let it drive through this and see how it behaves.
Yeah.
The wood walls,
Yes,
they're not
the
tall
best
enough
thing
to.
do- Sorry?
They're not tall enough
Yeah,
for
this
this
you
to read.
cannot get any information regarding the performance of the system. The best thing to get accurate performance is to run this in a system where there are walls right and left, so to assess the lateral performance and front performance itself.
Well, this is more for more for like a predetermined course. This is more for someone who's driving an undetermined course that if something's gonna hit it.
Driving, that's,
It's supposed to
But
be
the-
implemented in a
yeah.
actual car that you drive.
Because that would be saying it's gonna give an actual predetermined course. This is if it's you're on the open road, something comes and hits you, it's gonna move out of the way.
We couldn't simulate an actual person controlling the car, so we had to make it autonomous.
Yeah, because
But there are, the sensors on the sides are pointed in these directions. So if you notice, if you can rewind the click of that video.
yeah. The point is that if you're driving and someone comes and hits you, or you're gonna hit a wall,
yes, it hits the system, guys.
It-
Hit lateral, you see lateral collisions and front collisions.
It's not actually hitting the walls, I'm
Yeah.
telling you. It's,
Here, immediately.
Come on. here, did not touch the wall.
yeah.
And
So it
what?
knows.
Yeah.
Yeah. No, it's not. It's from the camera angle. It may look that way, but
It's really not hitting the
Yeah.
wall.
You know better than me because you were there.
Okay, thank you.